Hi guys, this is Abaqus. I hope you're doing well. And here in this video, we are going to learn how we can simulate ENF specimen. As you know, ENF is the abbreviation of end notch flexural or end notch flexure specimen, like this. This kind of specimens are using more to get the energy release rate on the shear mode, and most of which this kind of tests are used in the adhesive joints. As you can see here, this is a joint, a pair of beams that stick together in a side, and also it has a crack or unsticked area here, and this specimen goes to flexural or bending testing method, which the most important of this kind of bending tests include, for example, 3-point bending. We are going to simulate this kind of specimen here. The paper that I have chosen for you is this paper. This paper is written by my friend Safar, and also this is a paper from my elder team with supervision of Professor Lucas da Silva. So first we are going to model ENF specimen in the here in the Abaqus software. Here I have written below the dimensions of this specimen here, and I'm following these dimensions as well. Okay. In the Abaqus, first we have to go to the part modulus and create part. This part is, let me name it as ENF, which is a 2D planar and deformable shell. Let's say this one 400. Continue. Okay, let's create lines using this icon. Click on this, and the first point that I'm going to start with is 0 and 0. Okay, and from this point I'm going to draw my sample like this. As you know, this length is for the unsticked or unbonded or the cracked size of the DCB, of the ENF specimen. Then we have to add some constraints. The first important is the fixed one. I'm gonna fix this point, and now I have to apply some equal lengths. For example, these two lines are equal, and these lines as well are equal to each other. These two lines are equal, and the adhesive thickness also is equal. Nice. And now we have to apply the right dimension. For example, here is 300. Here is 10. Adhesive thickness is 0.4, Nice. And also here is the crack length, which is 50 and 60, 110. So here this length should be 110. It's okay. Now this geometry is fully defined and turned to green, as you can see. Okay, everything is done. We can exit from the sketch part, and now we have to add some partition here. You can use partition face and then create line and draw these lines as the adhesive layer. Okay, done. Okay, you can see the model divided to 3 parts. 2 parts are the adherent, and this layer is the adhesive layer. So now we have to also create another part, which is the fixture part. We have to click on create part, and here I'm gonna write fixture, which is 2D planar, yes, and discrete rigid for this one. And you can click on continue, and just we are going to draw a circle, simple circle like this. Just draw it from the center, from 0 point, and apply the dimension. The radius is, for example, 5, like this. Now I'm going to the assembly part directly to assemble my model. So create instance and choose these 2 parts and click on OK. So now I have to transfer this rigid seam to the right position. Let me check. The right position is 50 here, and since it's in the 0 point, it should go to -5 in the y direction. So click on transfer, choose this one, and the first point is 0, and the second point should be 50, -5. It's okay. I have to insert another part and transfer it, and also this one should go here, which is 250. Okay, let's say 250, -5. Sorry, the first point should be 0, and the second point 250 and -5. Okay, and the third one should go It's simple. You only have to click on this node as a first node and this second node to transfer it like this. Okay. Now we can go to the property modulus and apply our material. The first one is aluminium. The aluminium has the elasticity property of let's check. yeah, here 71 gigapascal, and it hasn't any Poisson ratio, then we consider it 0.33 maybe. So here 71 3 zeros, and here 0.33 maybe. It's okay. And then adhesive property as well, mechanical elastic. The adhesive or the CZM elements should follow the traction separation law. Then you have to change the type to the traction one, and here you have to enter the elastic modulus in the first and the second and the shear direction. So let's check here. The modulus is 2483 for the tensile one, 2483 megapascal, and maybe 1000 for the shear one is enough. Okay. Also, we have to add the damage properties. Sorry. Choose the adhesive again. Now we have to insert the damage properties of the adhesive. So if you go to the article, here you can see that the ultimate tensile is around 38 and 38 megapascal, which is the maximum stress that the adhesive can bear in the simple tensile test, and also the amount of energy release rate on the second on the shear mode, which is here for this type of for this method of extracting G2 is 0.15. Then we are going to simulate this one. First we have to insert the damage of traction separation law and choose the quads damage. This is the ultimate stress, which is 38, 38 and 38, and also we have to use the damage evolution, change it to the energy, and use the power law, select power equals to here I was to say that the energy on the first mode is not important, then insert 0, but in the second mode, as you can see in the paper, it equals to 0.15, and click on OK. Also, it's better to insert the damage stabilization coefficient, which is the viscosity coefficient. This is a short amount, as I already told in my Paris video. You can insert 0.001. Okay, now it's okay. Now we have to create section. The first section is aluminium, which is solid homogeneous. Continue and choose aluminium. Here is a plane strain with thickness of 10 millimeter. Okay. Another section, which is adhesive, which is the cohesive element. Continue, and material assign adhesive and response traction separation, and autoplane thickness is also 10. Okay, now I have to assign these sections to the right position. Click on this icon and choose this side and select aluminium. Okay, it turns green, and also choose this layer and choose the section adhesive for this area as well. Okay, now we can go to the step modulus and create a step. This is a static general. Click continue and turn on non-linear geometry and go to the incrementation, and here let's say 0.1 as initial and 1e minus 50 as minimum, and let's say 0.2 for the maximum one. Okay, also you have to manage field output. Edit this one because we want to get some other outputs. First of which is this one, status, which shows the status of the CZM elements. Also, it's better to get STEG, which is the amount of degradation or D parameter or damage parameter in the CZM layer, CZM elements. If it reaches to 1, then it means that this element should be vanished. Okay, and this is a parameter between 0 to 1, as you know. It's okay. Now we can go to interaction. Sorry, I have to go to the part modulus and say something that I have forgotten. Go to the part modulus and choose the fixture part. Here, when you create a rigid seam, you have to make a reference point for this part, and that's because this is a rigid part and it is not deformable. Then you can then you can assign its movement exactly using a node or reference point. Sorry, the right word is the reference point. So go to the fixture part and use tool and reference point. Now you can select, for example, this center as a reference point. It's okay. Now you can go to the interaction. Now you can see that the reference points are the representative of these rulers here. Now in the interaction part, we have to create the contact between these rulers and the beam. So click on create interaction here, and it's a surface to surface contact. Click on continue. For example, for this one, choose this ruler seam as a master surface, and then go. It asks you that which side is the contact side, which is the yellow one, and then we are going to select a slave, which is here. Now we have to add the property of interaction, our interaction. Click here, and it's a contact, and let's introduce a simple hard contact for this one. click OK. Okay. Similarly, I have to apply for these rulers and the contact, and I have to introduce the contact between these two features. So interaction 2, here is the master surface, the yellow one, and here is the slave. I already add the properties. Okay, another one. Okay, now the contact between these fixtures and the ENF specimen is introduced, and also one thing is better to do here, which is the introducing or creating the interaction between these two lines, because as we apply the load here, maybe these two areas go to each other, and that's the thing that we don't want to. And then create another interaction, for example this line as master and this line as a surface, as a slave one. Okay, as you can see here, also we create another interaction. Now we can go to the load part. In the load modulus, it's important to apply the right load, right boundary condition. Click on create boundary condition and choose Incaster. Choose these two reference points and select Incaster, and also choose this reference point and choose displacement rotation and choose this reference point. Now we have to apply, for example, -2 in the y direction, and also we are going to bond this ruler's movement in the x direction, and also we are going to bond it as for the rotation movements. Click OK, like this. And also to neglect the rigid body motion of this ENF specimen, we have to bond it, for example, from this point. Click continue, choose this node, this point, and here as you can see, this is bonded from the y direction. Then the only direction we are going to bond, for example, is U1 and the rotation 1. We no need to bond it from the y direction. Okay, like this. Now we have go to the mesh and choose the part. For the rigid seam, you only need to mesh like this, simple, and it turns green, as you can see. Now we can go to the ENF part. First, you have to change the shape of the elements using this assign mesh. Change to quad and structure. Okay, it fully turns to green, which means that the software is able to mesh it using using rectangle shape. Now choose this icon, select the aluminium parts, and the aluminium side should be plane strain. Click OK, and this layer should be cohesive element. Use the maximum degradation, for example 0.98. If the D parameter or damage parameter reaches to 98, then the software goes to remove this element. And also you can select this element delamination. Okay, and use one ply. It's okay. Mesh it. Now I had to go to the job. Okay, now we can create a job in the job modulus. Click on create job and create, for example, ENF job here. Click continue and click on OK. Then let's submit it to the software. Let's monitor it. Now it's starting to solve. It goes very well. Now it's completed. Okay, close this window and go to the results. Now we can see the results. Okay, let's let's view the animation. As you can see, something like this, and let's slow down it. Okay, also you can see how the crack is propagating. For example, let me change the parameter to the S-tag. As you can see here now, it is blue. The CZM elements are blue, which is the 0, and if it goes to under shear, this elements also turns to red and they are vanish. And you can see these elements are also more than 0.98, then they turns to red, which means that these are vanished elements. Also, we can check from this. Okay. The important part in the ENF test is to verify the load amount using the experimental one. So for this we can get the load and displacement of this point. So let's get it from the software. You have to go to the create XY data and ODB field output, select this one, click continue. You have to change the position from integration point to the unique nodal and select the reaction force on the y direction, and also the u or displacement from the y direction. Say then you have to go to the elements and nodes and edit section, choose this reference point and save it. Now the reaction force and the displacement of y direction for this point saved in the software. Now close this window and go to the operate XY data. Click continue. Here we have the reaction force on the y direction and also displacement on the y direction. So we have to combine these two data. Click on combine and select first U and then reaction force, and save this as, for example, displacement force. Okay. Now close this window and go to plot this displacement force diagram. Okay, as you can see, the load is increasing, then it reaches to this point, and in this point the load is decreasing because of the crack propagation. You know, this amount is very important for us in the ENF tests. So here, if we get the data of this point, we have to click on this diagram, which is almost this point, 1395. It is shorter than 1 and it is more than 0.75. Yeah, should be this one. Minus 1395. Okay, the important thing is to verify this amount using your experiment. So we go to the paper, and here the simulation that we made is this dash line and green line. This is, and the force here is almost more than 1300, which is a good verification for our work. I hope this video will be productive for you. Thank you very much. See you later.